In this video, we want to continue our examination of satellite navigation, looking at the signals and how it is that you can use one radio frequency channel to talk to 24 different satellites. Let's review the learning outcomes. Then we'll look at the GPS system and navigation message from the previous video. We'll figure out how we can transmit binary data with what's called binary phase shift key approach. We'll then talk about how you do spread spectrum transmission using what's called direct sequence spread spectrum. And to do that, we'll need to be able to generate pseudo-random number sequences. That is, they look like random numbers, but they're not really random numbers. Finally, we'll look at the GPS signals and their timing, some updates to the GPS since the navigation method framework and the CA method, and then augmentation services, so how we can get improved position using some known positions. We'll summarize and look at what's next. So to review the learning outcomes, when you finish the module, the student should be able to name the segments that comprise GPS. Remember, that's the space segment, the ground segment, or control segment, and the user segment. Explain the principles behind GPS, including how many satellite signals have to be received to estimate the user's location. That's that idea of intersecting spheres. So two spheres intersect, you get a circle. Another sphere intersects, you get 2 points on the result. And then you should be able to disambiguate one of those if you're on the surface of the Earth. You may need an additional measurement if you're in space, but if you're near the surface of the Earth, you should be able to disambiguate. And then you need one to correct the timing measures, because the user's clocks are not as good as a satellite clock. So it takes at least 4 measurements to get started and 3 to continue once you get your clock synced up. Pseudo range was a term that applied to the user estimation of the distance to the satellite. Since our clock was crappy, our estimate is bad relative to what it would be if we had an atomic clock locally. So it's a pseudo range instead of the true range. We want to talk today about how the GPS satellites will transmit on the same frequency but be distinguished, and then these gold codes or maximum length sequences, how they're used in GPS and how they're generated, and then how the augmentation services work. So we have the GPS constellation, which is the full set is the 24 satellites in 6 orbital planes, each at a 55-degree inclination. They're all 4 satellites in each one, and each is in 6 planes, so they're 4 hours apart as far as the Earth rotates. They're in a twice daily orbit, so they go around twice for every rotation of the Earth. They send the time and the location of the satellite to the user in the navigation message. We saw previously, we need the 4 satellites and then the 3 after you get going. And they have the model of the Earth built in, which is the WGS-84 that we discussed previously, and then some knowledge about the variation. So the navigation message we talked about, it's 37,500 bits long. It takes 12.5 minutes to transmit. It's set up in 25 frames. Each is 1,500 bits long, so each frame takes 30 seconds, and each frame is made up of 5 subframes, so each one of those takes 6 seconds. But the basic bit rate there is 50 bits per second, so a bit gets 20 milliseconds of time before the next. The subframe in each frame, the first frame has to do information about the satellite. We saw that previously. The second and third frames have the current ephemeris data. That's the location data for the satellite. Its attitude, where it is in its orbit, where it is probably the XYZ coordinates in the EFEC, Earth Fixed or Centered Frame, and the like. The subframes 4 and 5 change from each frame. So even though they're repeated multiply within each frame, each subframe, or each frame, subframe 4 and subframe 5 are different. So in the first frame, subframe 5 has information about service vehicle 1. And in the second frame, subframe 5 has information about service vehicle 2, etc., all the way up to the 24th frame when it has information about service vehicle 24. And then in frame 25, you get the almanac reference time. Similarly, the subframe 4 from the first frame has information about service vehicle 25, and this goes up through, it says 32, even though we'll see later there's only 30 distinct codes we can use, information about universal time and the like. And so those get updated. Those are repeated within each. They only come around each particular subframe called a page only comes around once every 12 and a half seconds. So we just walked through most of this stuff here, and we'll move on to the next slide. So we want to be able to transmit binary data. So we're going to, the navigation message is a sequence of bits. Each word in the subframe was 30 bits long and the like. The bits come in at every 20 milliseconds. You get a new bit, and eventually you get all these and you put the message back together. And we're going to use an approach called binary phase shift key. And so here in the upper panel, you see a binary message 100110101. And we're basically using a kind of, we're indicating this with amplitudes, if you will, but we could have an amplitude of 1 for the 1 and an amplitude of -1 for the 0. And so if we multiply this by a carrier frequency F naught there, then when we have a 0, we're going to send minus of that. And that makes what you see at the transition there from 1 to 0, how the sine wave's coming along. We've got this example here, the bits are coming along once every bit, but the carrier is 5 times a second. And so we see in that first bit, we get 5 full cycles of the sine wave. And then when we get to the 0, we multiply that by -1. And so now we get what's called a phase reversal there. The phase reversal where, again, at the transition from 1 to 0, the second period representing the 0 is now a minus SINE waveform. You see from 0 to 0, there's no phase reversal because it's the same bit again. But then when we go from 0 to the 1, at position 3 to position 4, then we see another phase reversal, and representing the 1, we have the positive amplitude sine wave. Again, no change as it goes to the next one, but when it goes from 1 to 0, then you get the 180-degree phase reversal. So this in this scheme, the bit duration is always an integer multiple of the period of the underlying sinusoid, or we get an integer number of sinusoids cycles per bit. We can talk about the spectrum of a signal, which is how much width it takes up in what's called the frequency domain. We all have a concept of frequency with low frequency, high frequency. And so when we send these square pulses, that causes a shape in the frequency domain that is this shape you see in the lower panel here. It's formally the shape of a sine x over x function squared. But the result is that there's a large amount of energy in the frequency world centered around the carrier frequency. That's indicated by 0 here, but this would be translated out to the carrier frequency of the signal of interest. So in the case above, it would be centered on 5 hertz. And then the width of this thing, you see the 0 crossing 0 at 1 over tau, 2 over tau. That tau is the width of the bit in time. So again, this would be centered at 5 hertz and 1 over 1. So 1 hertz to the right and 1 hertz to the left. So we have basically 2 hertz wide, twice the 1 over the duration of the bit for this bandwidth that we're occupying there. The concept there is that if we make the bits shorter in time, they're going to be broader in frequency. So you see that the tau, the 1 over tau shows where those lobes, those bumps in the spectrum graph there, those are going to get closer. As we make tau smaller, those will get further apart. And to make tau smaller, that amplitude of the peak there will get smaller too. So if we run things at a faster bit rate, we get a broader spectrum. And so we're going to try and see how can we exploit that. So direct sequence spread spectrum, or DSSS, we use a pseudo-random noise sequence to generate a sequence of binary numbers, either 0 and 1, 0 and 1, but we'll often assign -1 to 0 and 1 to 1, etc. So we can use one of two ways of this. If we think of the sequence of numbers as -1, 1, -1, 1, -1, -1, -1, 1, 1, when we multiply it by itself, no matter what we do, we're going to get it back 1, 1, 1, 1, 1. So this sequence of numbers that has a nice property that when we multiply it by itself, it goes away. So if we were to actually take our binary signal, which is shown in the upper panel here as the blue line, and that's what basically has the spectrum below in the blue lump. So there's our binary signal. Now we have this faster signal that also looks like our binary signal, except now it has no information. It's just a bunch of random ones and minus ones. So when we multiply the 1 times minus 1, we get a minus 1. When we multiply the 1 times 1, we get a 1. And so you can sort of see how the red signal times the blue signal could be transmitted in the same way that we transmit using binary phase shift key. But we also could, if we could get that random noise sequence back, then we can multiply it and it'll just go away and we're left with the original bit message. So these faster signals here are called chips. They're a pulse. They're a fraction of the bit duration. So the chip duration is smaller. The chip rate is higher. And this is what's used to generate the C/A, the course acquisition code. It's called a pseudo-random number sequence. And this CA code is going to be a PRN, a pseudo-random noise sequence. And we want to see how we can generate that in the next slide. But we're going to combine it with the message. So we're going to, if we're talking binary, 1s and 0s, we're going to use an exclusive OR operation. If we've already got our message as 1 and minus 1, then our chips are going to be 1 and minus 1, and we can do the multiplication. These chips are coming in fast, and they're little and short, and they're going to make the overall spectrum of the product sequence here, what we're actually going to transmit when we combine the message with the chips, look like the chip spectrum. And so as we go faster chips, we get a broader spectrum, and that's shown by the red line in the panel below. And eventually, if we use a fast enough chip rate, we can actually hide our signal in the noise. We're going to have ways to get it back using these same chips. Not only can we multiply the chip sequence by itself to get 1 in every instance, but we can also find the chip sequence by comparing with other chip sequences. These are going to be very distinguishable. So how do we generate these chip sequences? That's sort of the next activity here. Well, these pseudorandom numbers, for binary pseudorandom numbers, can be generated using a shift register, which is the square box there shown with the data in and the Q0, Q1, Q2, Q3 in the clock, and what's called an exclusive OR gate. The exclusive OR, you will hopefully remember, has the property that if the inputs are different, like an OR gate, then you get 1. So 1 or 0, 0 or 1, the answer is both 1. But unlike the OR gate, where 0 or 0 is 0 and 1 or 0 is 1, here the exclusive OR, it's only 1 when they're different. So if both, in this example, upper panel here, if both Q2 and Q3 are 1, then the input to data in will be 0. And if if one of them is a 1 and the other is 0, then the input to data in will be 1. And we move this at a clock. So this happens every so often, tick, tick, tick. So if we had all zeros as Q0, Q1, Q2, Q3 here, it's not hard to imagine that we would just get 0 back, because the exclusive OR of 0 and 0 is 0. And so nothing's going to change there. They're not different, so they're not exclusively ORed. And so we put a 0 in, and we just keep feeding 0 through the whole system. So once the system gets to all states Q0, Q1, Q2, Q3 are 0, then it's just going to say 0 forever. On the other hand, if we start with all 1s, then you'll show in the exercise that you can reach all 15 other states. So it'll start with all 1s, it'll reach all 15 other states, and then it will repeat. And that's what's called a maximal length sequence. When you have something that is an n-bit shift register, then you can generate a 2 to the n minus 1 long maximal length sequence. In this case, it's going to be a 15-point sequence, because our shift register has 4 bits. 2 to the 4th is 16, less 1 is 15. These are also what are called the gold codes. Now, not all combinations are going to be maximal length, and so the other exercise you can do will be to show that if you did the exclusive OR of Q1 and Q3, then you don't get a maximal length sequence. So there's only so many of the possible sequences here by combining, using exclusive ORs between Q0, Q1, Q2, and Q3 that you get a maximal length sequence. For the GPS satellites, the pseudo-random noise sequences are generated using a 10-bit shift register. So 2 to the 10th is 1024, so our maximal length sequences will have 1023 states. You can show that there are going to be 60 possible maximal length sequences. The rest of them will not be maximal length. And of those, 30 are just mirror images of the other 30. So there's really only 30 unique sequences that we'll be talking about here. So two of these unique sequences are shown on the panel here. The first one, the one that says G1, and it has the outputs Q3 and Q10 going into this modulo 2 addition, which is the same thing as exclusive OR, right? 1 plus 1 equals 0, carry a 1. But if you're doing modulo 2, then you just get the 0 back. And 0 plus 0 is 0. So exclusive OR implements a modulo 2 addition, but sometimes you do that over, as you see in the lower shift register combination, you do that over more than 2 outputs. So in the upper shift register, we're taking 2 outputs, Q3 and Q10, combining those with exclusive OR and using those as the input. And we're also taking the output of Q10, what's called the G1, the gold sequence 1, and it's going into another exclusive OR. We can show exclusive OR with the OR gate with the line on it like we had in the previous slide, or we can show exclusive OR as a circle with a plus in it where the plus fills the whole circle like that. But what's different here is we don't just take these 2 shift registers and combine them. We take the selected outputs from the second shift register, and we combine those using exclusive OR to get the output. That's what's used as the G2 sequence. And that I there is the service vehicle number. So we're going to combine 2 different outputs, and this was discussed in the reading, 2 different outputs for every service vehicle, which will give us a different overall pseudo-random noise sequence. Again, it's going to be 1023 states long, but it's going to be a different one for each of the service vehicles, yet we're going to use these same 2 shift registers to build all these different sequences. So that's one of the nice things here. We don't have to change the technology to implement the gold codes. We just change what we add together to implement this final pseudo-random noise sequence. So there are again 1023 states of each of these outputs, and we XOR them together. And these can be XORed with relative delays. That's what the picking the 2 different outputs, we're basically picking them with relative delay. So we end up with a lot of different CA codes that could possibly be used. But again, we're only picking the ones that relate to our service vehicles. And this is the same approach. So we're going to generate this noise signal, and you'll see on the next slide how we're going to use it to modulate as part of the binary phase shift key. We're going to use that as our what gets modulated to do the binary phase shift key. So we're going to send out this noisy signal with all these chips that have screwed up our bits. But the trick is that these CDMA sequences, these DSSS sequences are recognizable. The sequence that goes with a particular service vehicle is distinct from a sequence that goes with another one, and it's not hard to figure it out by comparing them over fairly short lengths. So it's not indicated on any of these slides, but there's a way on the reception side to figure out which pseudo-random noise signal you're looking at, since you know how to generate all of them, and just comparing them by just basically moving the taps on the output of the second shift register. Say you're taking Q2 and Q6 on the first one, then for the service vehicle 2 you would take Q3 and Q9, and then Q4 and Q10. So they're just using a 1 tick delay, and yet you get a different pseudo-random noise sequence that way. And again, we can distinguish these quite readily, and that's going to make it valuable to picking the signal we're interested in out of the noise. So in this, we've already generated in the panel on the right, we've already generated the CA code. It runs at 1.023 megabits per second. That's 1023 megabits. That's the length of the sequence per every millisecond. right? So the bits are coming in with a duration of 20 milliseconds, but the CA code has a duration of 1 millisecond, so it repeats 20 times under every bit. And that's part of what gives us the time to figure out which CA code we're looking at. So we take the CA code and the navigation message and we XOR those together, and then that's the signal we use to feed into the BPSK modulator that's going to modulate this L1 carrier, which you can see there is 1572.42 megahertz. There's a relationship in the clock speeds between the various carrier frequencies used in the GPS. They're all related. They're integer multiples of another clock speed that's related to the atomic clock on board. Each of them has its own quartz crystal to determine its own oscillator frequency, but those are synchronized using the atomic clock on board the GPS satellite. So now that we've got that, we can also talk about that's the civilian channel. That's the historic civilian channel as used. But we can also talk about the military channel. The military channel uses a faster and longer gold code. So here, the military channel, it runs at a rate of 1023, 10 times faster as far as the chip rate there. So now, instead of having at every 20 milliseconds, instead of having 20 repetitions of the code, we're now going to have 200 repetitions of the code. So now we, if it's 1,023 points long, if it's a longer code, we may not have the repetition. I think I stated it was longer, and I'm not absolutely positive about that, to be honest. I recall reading that, I believe, in bins, that the P code is a very long sequence. Anyway, so we do basically the same kind of thing. We're going to take the P code, which is another pseudo-random noise sequence, and we're going to XOR it with the navigation message here, and we're going to combine that. We're going to use that as a BPSK modulation for the L2 carrier at 1176.45 megahertz. We also put the P code onto the L1 channel, and this is not to say that you do the CA code modulation and then you again modulate it with the P code. I think these are both put together separately, and they're both just transmitted at the same time. The P code can also be encrypted. That's a piece of POI code. So the receiver coming in now can try the pseudo-random noise sequence for every service vehicle and find, again, these pseudo-random noise sequences have the property, if you compare them to each other, when you compare the one to itself, what's called the autocorrelation, you get a large number, and when you compare it to the other pseudo-random noise sequences, the cross-correlation, you get a small number. So we can identify which one of these signals we have, and once we pick it out, we multiply, we get it, and we get the time sync right, of course. Then we have to multiply it again, but then we multiply the chips times the chips. -1 times -1 is 1, 1 times 1 is 1, and we just get the navigation message back. So that's sort of the concept of how the demodulation works. So we think about the timings involved now. The handover word had a 6-second resolution because that was coming in on every frame. The subframes each came in every 1.2 seconds, but inside the bits in each one were 20 milliseconds apart. So that gives us a 20 millisecond resolution, which is not good enough to come down that close. The pseudo-random noise, though, repeats 20 times per bit, so that gives us a 1 millisecond resolution if we can figure out how rapidly the pseudo-random noise is repeating. But now if you can figure out the timing of the chips, then that's a duration of 978 nanoseconds. So now if we're estimating the chips down to 978 nanoseconds and we're correcting based on that, we can get down to a few nanosecond resolution, even with a crappy megahertz kind of a clock in our phone or whatever. So we can actually get improved timing here by using the chips that are coming in very fast. There's other GPS. We talked about L1 and L2, but there's the L3, L4, L5. L referring to the L band of the electromagnetic spectrum. So the L3 channel is used for the detection of what's called high energy events. If there are nuclear explosions on the surface of the Earth that will emit certain electromagnetic waves, and then those will interfere with the L3 channel signal, and so those can be used to detect. So this is used to monitor compliance with the nuclear treaties and things like that. The L4 channel is largely used to study propagation through the ionosphere, and I don't think there's any information still on that channel. But the L5 channel, which is historically called a civilian safety of life signal for use with the emergency responding and the like, has been, there are now what's called the new CNAV message, which is a civilian navigation replacing the C/A or operating in addition to the C/A. Which is a packet-based kind of transmission, more like how communication by Ethernet, internet works. And so each, it comes in 300-bit packets instead of 300-bit subframes. And they're very similar. Each there's a preamble, the service vehicle number, but then there's a code for what kind of message. We still get the time of week information. But the message can tell us what to do with bits 39 to 276, those 238 bits of data there. And you can send the almanac, you can send the ephemeris data, you can send the service vehicle health, you can send ionosphere corrections and the like. So it's a more generic messaging system where you don't have to send information at fixed rates. You can send them at particular times when it matters, and they can you can even have multi-packet messages, and the system can reconstruct them. And so that's this new CNAV message. Was first introduced on L2 channel, and that's called L2C, but then it was also introduced on the L5 channel, that's L5C, I'm missing a C there, and then on the L1 channel. So this runs on multiple channels, and this gives civilian receivers a chance to do the kind of thing that the military receiver does between the L1 and L2, comparing propagation delays, and so you can get improved understanding of how the signal propagates through the ionosphere and improve resolution that way. Augmentation services, even though we've got pretty good resolution now with our GPS, the default standard is not good enough to do more than Category 1 instrument landings. And so by having some known receivers at surveyed points, known points, we can measure what the GPS system is saying those points are. So in this picture here, you see four reference stations on the ground, and you see a moving reference station, the GPS rover receiver. So these are all moving around here, and the reference stations are fixed. We know where they are, and so we're getting information from the GPS, and it may not tell us exactly. So it may be taking the reference station, you're here, and the reference station says, no, I know I'm actually right here. So with these corrections, we can understand better about the signal propagation and what kind of time delays are involved and what kind of errors are involved. And those all go to this network control center here. And from that comes a signal that goes to is uplinked to a geostationary satellite. And then there's a message sent from the geostationary satellite to users so that they can improve their position using these augmentation services. This is an instance of what's called a space-based augmentation service. There's also ground-based augmentation services. So in a ground-based system, instead of uplinking the data to a geostationary satellite and then sending it back to users over a separate channel, you would have a local transmitter near your airport. And with the augmentation services, particularly locally based augmentation services, then you can get down into the kind of meter precision or less, and you can then enable Category 2 and Category 3 instrument landings. So the illustration here is what's called a wide area augmentation system, or a space-based augmentation system, where we get the information from ground-based reference stations, but we send that to a satellite so that it's available to a wide range. And this is used for broad geographic areas, like the mid part of the U.S., eastern U.S., western U.S., and the like. Whereas the local ones are particular to airports in particular geographic regions, so not that wide. And that's pretty much the whole story. So we saw today how GPS uses direct sequence spread spectrum for code division multiple access, code division compared to time division and frequency division. On all 20, so you can use all 24 satellites transmitting on the same channels. It's the same thing as your wireless uses, your wireless phones, etc. The CA and the PY codes are generated with these maximum length sequences, and these are implemented with the feedback shift registers, where we're feeding back combinations of the bits in the shift register using exclusive OR gates or modulo 2 addition. The legacy navigation message is on the CA code on L1. The military uses the PY code on L1 and L2. You can see the different chip rates there. So the military has a better temporal resolution immediately just from using the faster chip rate. And then the new CNAV messages are on L1, L2, and L5. Finally, we saw that augmentation services provide improved resolution by using known locations to be able to correct errors. So that's sort of it for satellite navigation. We got one other area of sort of navigation to finish here before we can move on to talking about how we actually get stuff implemented into the system, and that's surveillance and radar.